In this third item, we have a rigid bar, ABC, that is suspended or is hung from two rods. We have a 10 kilonewton force out here at the tip, and we're asked to ultimately find the vertical displacement at C. We're going to ignore any yielding or buckling or rocking sideways of the system. So in other words, there's some sort of restraint that prevents a swing action going on. So we might, as our very first step, consider starting with a free body diagram, and we're going to do that of the bar ABC and make some guesses about what we think are going to happen. That we have the 10 kilonewton force acting down, we have the rod force at B that most certainly is going to be acting up. But if we sum moments about C, we can see right away that A actually has to be pushing down. So we get an interesting situation that you might think that you're going to have pure tension in both rods, but you will not. One's going to be in tension, one's in compression. That's something to take note of as we move along. We're going to ignore that buckling that might happen in rod A. Is at least one thing that's important to take note of. All right, let's sum moments about A, and let's take clockwise positive, and we'll get 7. Oops, I said that was C. That's really supposed to be B. So 7 times B minus 9 meters times our 10 kilonewtons equal to 0, so therefore B is equal to 90 over 7 kilonewtons. And that positive sign says we guessed right, that's in tension. If we sum moments about point B, again, let's take counterclockwise as positive. Now we get 7 times A minus 2 meters times 10 equal to 0, so therefore A is equal to 20 over 7 kilonewtons. So the fact that we can find these forces through the static equations of equilibrium alone, that arrow does not indicate a direction, that's just to highlight where the answer is for the force in A and B, tells us that this is a statically determinate system. Now our goal is to figure out what the displacement at C is. We have two flexible members or springs, those two vertical rods, so now we got to go figure out what the deformation is of the rods, and we'll use our common force deformation relationship, that delta equals NL over AE, and so the displacement at A is going to be caused entirely by the deformation of the rod. Note that because that's in compression, we know that that displacement is going to be up, right? That's in compression, so that's going to get shorter, and so that will be our 20,000 newtons. Notice my change in units over 7. That's our force in A times the length. That's 12 meters. I'm going to guess that I'm going to want that deformation in millimeters, so I'll just go ahead and move that on out. That's our length over our area. Let's see, we have cross-sectional area of each member of 40 square millimeters. So note, Newton over square millimeters is the same thing as Pascal, and then times 1 over our modulus of elasticity, which is 207 gigapascals, or 207,000 megapascals. So that's good to note, because Newton over square millimeters is a megapascal, so those will cancel out. The answer we get here for the deformation and then the displacement is going to be in millimeters, and that will turn out to be 4.14 millimeters. Let's just double check that real quick. 20,000 divided by 7 times 12,000 divided by 40 divided by 207,000, and yep, 4.14 millimeters, and that is going to be up. Right now, for displacement at B, that member is down, or it's in tension, so the displacement is going to be down, and that deformation for that one is 90,000 newtons over 7 times a different length, 8,000 millimeters. The area is 40 square millimeters. We got 207,000 again for the modulus of elasticity, and that's going to be 12.42 millimeters down. And so that member has elongated. So we get a displacement pattern, grossly exaggerated, that looks something along the lines of this point A has moved up by 4.14 millimeters, B has moved down by a lot more at 12.42, and so my scale isn't terrific, but we get something like this for the movement of that bar. Okay, so let's take a closer look at that. We're trying to get that delta C, and let's put a baseline in from A to C. We've got, again, something that goes up at A. There's your 4.14. At B, it goes down by 12.42, and then we're trying to figure out what the value is out here at C. And so there's a lot of different ways that one could do this. It is a similar triangles. We don't know where the pivot point is. One easy way to do this is just to say, hey, look, let's create a new baseline that's 4.14 above what the original was. And so by similar triangles now, I can get this value y, and then all I have to do is subtract off to get to the 4.14, the rigid body translation that we did to get to what we wanted. Right, so that would be delta C is just going to be equal to y minus the 4.14, and the y value is going to be this proportionality. You've got that total height, which is 4.14 plus 12.42, right, is to 7 meters, because that's 7 from here to there, and then it grows by 9, right? And then we subtract off the 4.14, and when you do the math on that one, you should find out that our answer is 17.2 millimeters moving downwards is our delta C that we were searching for.